an illustrative example that I want to go over because it's going to let us better digest what is demand, what is volume served, as well as I want to talk about a very unique and very important things that HCM is able to do. And that is the determination of if our bottlenecks are active or hidden, and it is able to show you hidden bottlenecks because data cannot show hidden bottleneck. If you are looking into, your data provider, probe-based data provider, all these, companies, they cannot tell you if you have a hidden bottleneck. If you are a macro simulation user, Vissim, Transmodel, or whatever, they are not going to be able, the methodology is not going to be able to tell you where hidden bottleneck is. Uniquely, HCM can point it to you where your hidden bottleneck is. So I want to make sure that, again, I have all your focus for next 5 minutes or so, because I want to go over this, and I want for you to learn what is hidden bottleneck, what is active bottleneck, and how HCM basically, can identify that. So let's take a look at this example. It's a hypothetical example. I have just a series of basic segments to make it easy for us to discuss. I have 5 segments, and segment number 4, basically, I have 2 lanes. We have a lane drop there, and, in segment, between segment 3 and 4, and then lane add between segment 4 and 5. So I assume my per lane capacity is 2,400. That's going to give me 7,200, as you can see on this table, capacity for segment 1, 2, 3, and 5. And segment 4's capacity is 4,800. That's where basically it is coming from. Then here, basically, I have 300 passenger car per hour flow, demand flow that they want to go and basically get served through this facility. What happens is that 3,000 vehicles, they want to get served through segment 1, 2, 3, 4, 5. No matter what the capacity is, they want to get served. So that's why demand for all segments is 3,000. So 3,000 for segment 1, 2, 3, 4, 5. So you see it's in the table everywhere. Now, in order to see what fraction of this demand gets served, we need to compare it to capacity for every single segment. So for segment number 1, capacity is 7,200. My demand is 3,000. And of course, I have enough capacity to serve my, 3,000 demand. That's why volume served is going to be 3,000. Then the same story is for segment number 2 and number 3. Even for segment number 4, still I have excess capacity and I can serve all my 3,000 vehicle per hour demand. So that's why volume served across the board is 3,000. All the demand gets served. We have not hit capacity. We are dealing with undersaturated case. And if you remember, in undersaturated case, I told you demand is equal to volume served. There are 2 more MOEs that are reported when we do analysis in the HCM. One is basically demand to capacity. The other one is volume served to capacity. As you can see, both these numbers are less than 1, and that's what it means that basically we have an undersaturated case here. Now, let's make this example a little bit more interesting. Let's assume that now our demand is 6,000 passenger car per hour. So everything else stays the same. I have the same capacities for all segments. But the only change is that I have 6,000 passenger car per hour. What happens is that for segment 1, our capacity is 7,200, more than our demand. So all the demand is going to be served. So volume served is going to stay at 6,000. Then for segment number 2, the same story as segment number 3. They're all the same. Let's take a look into segment number 4. So in segment number 4, our capacity is 4,800 and our demand flow rate is 6,000, which is, more than capacity. What happens is that we are going to serve only to the extent that capacity allows us. Of course, I need to mention that we are assuming that there is no capacity drop. Just to make this example very simple, we are not assuming if there are any capacity drop, because if there are, so this number is going to drop more. So we are going to serve to the extent that our capacity allows us. And that's when volume served is going to be 4,800. So 4,800 is different than demand. So because we have congestion going on here, we have no bottleneck, activated bottleneck, and congestion, these two values are not same. And if we look into demand to capacity ratio is 1.25. It's more than 1. So whenever demand to capacity ratio in HCM is more than 1, that means that that point is a bottleneck. That's how we identify bottleneck. And then we look into volume served to capacity. That ratio is 1. That means that this bottleneck basically is metering the traffic. When a bottleneck meters the traffic, we call that is an active bottleneck because it's actively metering the traffic. And all the queuing and congestion basically is going to happen upstream. Again, I need to note that here we are not modeling that queue, so we are assuming like everything is very nice and clean in segment 3, and it's segment number 4, we have that congestion, but we just don't want to talk about queuing for now because we just want to focus on the bottleneck. But if this was a real world case, maybe queuing congestion spills back to segment number 3, and also it impacts volume served in that segment. But we don't want to. We assume that thing doesn't exist. Here, the biggest point for you to note is 1. Whenever D over C is more than 1, that means that we have a bottleneck. And whenever the volume served to capacity is 1, that means that bottleneck is metering. Of course, with the assumption that we have no capacity drop. If we have capacity drop, so for example, if we have 7% capacity drop, 0.93 means that this bottleneck basically is metering. Now, let's take a look into segment number 5. In segment number 5, capacity is 7,200. We have demand of 6,000, so we can serve all the demand. But we cannot do that because demand is not able to get to segment number 5 because it's being metered, in the previous segment. So all that volume served that they come into segment number 5, just to that extent, they're going to be served. So volume served for segment number 5, again, it's going to be at 4,800. So despite the fact that, we have a lot of capacity, just because traffic, that demand is not going to get to segment number 5, that number is going to stay at 4,800. So as you can see here, we are seeing, few points where D over C, or demand to capacity ratio, and volume served to capacity ratio are not same. That means that we have oversaturation. So, if those two numbers are same, that means that it's undersaturated. If one place within your facility they're different, that means that facility is operating under oversaturated condition. So here we have a more interesting case. So I have the same example as previous example. I have segment number 4 that I have a bottleneck with 6,000 vehicles going on. Now what's happening is in segment number 2, basically, let's say an accident happens, or, a lane gets closed. And what happens is that, when an incident happens, is that lane is closed. Not only that, if you remember from basic segment analysis, we are going to have a CAF that we need to impose here. So those open lanes, they are not going to operate as basically like a full open lanes. Their capacity is going to be smaller. As you can see here in this table, for per lane capacity is 2,400. That's why for segment number 4 we have 4,800 as our capacity. But for segment number 2, it is 4,500. So slightly less than what we have for segment number 4. So that's our capacities. Let's say that's given. And now we have the 6,000 passenger car per hour flow coming in. They come into first segment. Basically, we have 6,000 demand, 7,200 capacity. We have excess capacity. We are able to serve all that demand. So volume served is going to stay at 6,000. Then for segment number 2, our capacity is 4,500, demand is 6,000, and we are going to only be able to serve to the extent the capacity allows us to do that. So we are going to only serving 4,500. So our demand to capacity ratio is more than 1. That means that this is a bottleneck. And then volume served to capacity is 1. And that means that this bottleneck basically is metering. Then on segment number 3, capacity is 7,200, demand is 6,000, but only 4,500 vehicles are able to come to the next segment, and only they are going to be served. And that's why volume served stays at 4,500. Here is the most important part of this story on segment number 4. We have a capacity of 4,800, demand is more than capacity, but only 4,500 vehicles are able to get there for segment number 4, which is, we have enough capacity to serve all of them. That's why, they're all going to be served. Now, if we look into D over C, still demand to capacity ratio is more than 1. That means that this segment still is a bottleneck. But then volume to capacity ratio is less than 1. That means that this bottleneck is not metering. So when a bottleneck is not metering, that means that that's a hidden bottleneck. We are not going to be seeing any queuing on that section. So if this was, let's say, real world, we are like flying on a helicopter, like watching this, what's happening here, we are going to see all the congestions happening, in segment 2, and, queue spillbacks, spillbacks into segment number 1. But then once they leave segment number 2, they just travel fine. They go easily through this hidden bottleneck without any problems. That's why this bottleneck is called hidden bottleneck. If you watch data, data is not going to tell you that's a hidden bottleneck. If you do simulation, using any software, basically, you are not going to get that. HCM is able to pinpoint that you with this D over C value. So if you use HCS, you know where your hidden bottlenecks are. Now, you may ask, okay, so we're looking to operation of this freeway. Really, segment number 4 acts as a hidden bottleneck, but there's no problems with it because vehicles are coming and traveling through that. Why we should care about it? We need to care about hidden bottlenecks because once we fix active bottleneck, hidden bottlenecks, they're going to be activated. Think about it. So for example, let's say you are working on a real world freeway that has recurring AMP congestion, and then you are proposing, different scenarios, hey, to mitigate traffic. Like for example, you want to add a lane or, do whatever you want to do. If you fix capacity problem in active bottleneck, if there are hidden bottlenecks, they are going to be activated. And actually, sometimes the queuing congestion, the hidden bottleneck can be more severe than what is in the active bottleneck. So let's say, for example, your active bottleneck gives, let's say, I don't know, 200,000 hours of delay per day. If you fix that, your hidden bottleneck can give you a more delay, 300,000 hours of delay per day. So that's important to identify hidden bottlenecks. And when it comes to, real world type of, applications, to to fix active bottleneck, you make sure that, hidden bottlenecks, they are not going to be activated. So this was perhaps one of the most important points that I wanted to talk in this course, the difference between demand and volume served, and the unique ability of HCM to find hidden bottlenecks.